So yeah, sweet.
Okay, that work?
Yep. At least
Awesome.
so.
Whoa.
Yeah, so
I spent 3 hours on this picture last night.
Yeah.
It's beautiful.
So yeah, loudspeakers.
It was worth it.
Talk about them. So just a quick overview of what we're planning on looking at. We're just going to start a little bit more general with sound and audio, and then talk a little bit about terminology, set that establishment so that going forward you can kind of like understand the rest of the stuff. Then we'll go into transducers, enclosures, and a little bit of psychoacoustics because it's fun. So visualizing sound. It's very hard to like just picture sound, but all sound really is a wave, right? And so you get situations like this where you can kind of see like the waves coming off, and when you have a point source, the sound waves are just going like towards and away from it. That's all that sound is that wavelength propagating throughout. And then these are a few other like quick visuals of just kind of the impact sound has on the atmosphere around it, what that ripple looks like. Yeah, and then there's also the visualization aspect of somatics, where essentially you're running a frequency through a plane. And so like, let's say you put like water on it or you put sand on it. If you play different frequencies, the waves are going to settle a certain way where you can see the nodes and antinodes. And you can see that at lower frequencies, it's a lot more spaced out, a lot more simplistic. And then at higher frequencies, kind of see that those quick wavelengths kind of develop into this more complex pattern. And so that's just a pretty cool thing to show as well, is how that looks in a plane. So quite a few things actually affect audio playback beyond just your speakers setup. It starts as basic as just your brain, your mindset. Psychoacoustics, which, like I said, we'll touch on again a little bit at the end, is more of the psychology aspect of why you enjoy music. Sometimes it's just wanting to like or dislike the way that something sounds. Sometimes it's more about the color or shape, general aesthetic of something. And then sometimes, you hear someone's, of high stature say, oh yeah, this has whatever going on with it. And you just really pay attention to that. And you're like, oh yeah, it does. So there's a lot of aspects that can influence how you like something and whether you like something. It also depends on your audio source. There's different resolutions of music playback. If you're working with a more, physical playback system, there may be like a tape thickness, or maybe the quality of your vinyl.
To sort of elaborate on that a little bit, what I'm talking about there is with a record player, you have this little moving needle, and so the quality of that itself is a little transducer, and so it's the quality of that and how it's built can influence the sound quality. Tape thickness and speed is sort of like what we would relate to. It's the analog equivalent of bit depth and sampling rate. So kind of those are like the analog variants of what we now kind of are used to in digital, of sort of the depth of the sound, the bit depth of the sound, and then also the sampling rate. So yeah, sorry, just wanted to elaborate on that a bit.
Thank you. Yeah. So once you go on from the audio source, there's like this whole other, processing stage that happens before the music is actually played. We refer to that as amplification and preamplification. And so that's where you'll see a lot of distortion happening, specifically harmonic distortion. You'll see things happening with the signals themselves. Whereas once you get into the more acoustics end, it actually coming out, the signal manifesting itself into kinetic energy, manifesting itself into sound that you hear. That's where acoustics plays a huge role. And so what's the geometry of the room? What materials is everything made out of? Things as simple as like, what are the atmospheric conditions at the moment you're listening to this can play a huge difference, like between dry air and very humid air. And then also just the general vibes of the place, and that plays back into psychoacoustics. Yeah. So there's a lot that goes into it, and like things you wouldn't even think of, you know, the shape of your ear, the directionality of certain things, where things are placed. There's so many things that come to play when it comes to audio. And so, yeah, we just want to give you a quick anatomy of a speaker in its enclosure so that you can kind of see what that looks like. So every speaker will have a driver cabinet, and more often than not, crossovers or filters. And so you can kind of see like this cross-sectional diagram over here on the right. There's a little port right here. Can you see my mouse by chance?
Yeah.
Okay,
Yeah.
cool. So yeah, there's this like little port right here. You can see like where the wires end up hooking up to. There's a little tweeter, a little woofer. So
the crossover's that little green plate back there, and yeah, so the bass reflex design.
Yeah, so this all comes together to form its own sound. And there's other things that are commonly found. So like I said, this port right here, ports are a pretty common design addition. And then there's also this other list as well. And all of those can be used, but they're not quite as necessary. The main component is the drivers themselves, which are the speakers. And then before we go more in depth into like transducers and stuff, I just want to give you a quick overview of how sound is experienced as well. Just so you can have a general understanding of that if you don't already. So sound is measured on a decibel scale. And so you may have heard the word decibel used before. You might not know what that correlates to. So I included a couple of infographic diagrams here. So on the right, you can kind of see a scale of like, oh, 30 decibels is like, oh, I'm whispering to my friend. 50 decibels is it's raining outside. And then, you know, as you amp things up, you kind of see like the full range of things you're probably familiar with and can conceptualize, oh, that's how loud that difference is. And some of these differences don't seem equivalent, and that's because decibels are actually measured on a logarithmic scale. So something that sounds twice as loud to you actually contained like way more energy to produce that, more than double. And this bottom left diagram, it also shows you, I believe it was called the curve of equal hearing. So essentially what this one line is showing is that along this line is the intensity in decibels that something would need to be played for you to hear something at the same sound level, for you to perceive something to be just as loud. And so you'll see that at the upper and lower limits of your hearing, it takes a much higher intensity for you to be able to hear a really low frequency sound or a really high frequency sound than it would for something in the middle. So that's kind of what that hearing curve looks like. So you're not hearing all frequencies equally. In addition to the decibel changes aren't linear.
If anyone's familiar with like the A weighting scale, that you'll notice that's somewhat of the inverse of the A weighting scale, and that's what that's modeled after. Is that low frequencies need to be played louder to be perceived at the same volume. One little extra interjection here is that there is actually a theoretical limit to what the loudest sound can be, which is around 184 decibels, I believe, because since a sound wave is a positive and negative pressure, relative to sort of an average pressure of atmospheric conditions, um, eventually start clipping against the rail of vacuum, and so you create a shock wave, and that's why when you see sort of explosions or something that's extremely loud, that's over 180 decibels, the shock wave is the sort of the sound, the pressure wave clipping against vacuum, and that creates kinetic movement in the air. So I thought that was a fun fact when I learned that. But yeah.
Yeah.
Do you know if that maximum possible sound is specific to the medium? Like if you were measuring through water, would it be a different theoretical maximum?
Yes, yeah, it
Okay.
has to do with the compressibility of something. So water's a little different. It's a little funky because we like to think of it as incompressible, but it isn't. So, it's depending.
Yeah.
But it's generally sort of if you think about sort of a sound wave as alternating current, around I'm forgetting all of my EE terms here, but kind of like a sine wave, right? And so you've got your minimum and maxima, and so your minima is going to be your lowest pressure. So wherever your atmospheric condition is going to define how far you have until you hit the rail of a vacuum, depending on. So like in lower pressure conditions, it's easier to clip against that rail faster.
Okay, that makes sense. Thank you.
Yeah, and a fun way to theorize like compressibility too is you're essentially just turning air or whatever medium it is into a spring.
Mm-hmm.
So I think that's pretty neat, and it's like how stiff is your spring?
Absolutely.
Yeah. So yeah, then we have just some overview terminology for you guys in case you haven't heard it before. We may or may not use it later down the presentation, but they are good terms to have in your pocket. So the first one is sensitivity. It's the amount of sound per unit of power input. So it's essentially when you insert a little bit of power, how much sound is coming out. How sensitive is it is kind of how that is reasoned. And then damping has more to do with putting a stop to the sound. So it's reduction of a signal's amplitude after the initial impulse. That initial impulse, in our case, we're going to be talking about acoustic or kinetic energy. So a good way to like visualize damping is like if you've ever like had a ruler on the end of the desk and like just kind of like sprung it, or anything that's had any sort of spring motion, and seeing that the amplitude gradually decrease until it stopped moving. There's a lot of examples of this in nature because most things end up pretty damped. But when things aren't damped, that's when it becomes an issue for you when it's underdamped. And I believe we'll touch on that a little bit later. Then we have transient response. So transient refers to over a period of time. And so transient response is the ability of a speaker to respond to a sudden change in signal without blurring the sound. And this plays into group delay, which is essentially a specific phase distortion where different frequencies aren't all coming through at the same time. And so a common example of this would be like muddy bass. You hear the higher pitch slightly before you hear the lower pitch, and that kind of causes you to hear it out of phase with each other. It elongates that, but not evenly. So that's kind of what delay and transient response are referring to. Harmonic distortion is unwanted harmonics of the fundamental frequency being played through the speaker. So fundamental frequency is essentially the frequency where something goes from like that damped to underdamped. It will start to vibrate and the amplitude will pretty much just increase without control until it breaks. So generally, like even outside of audio, this is a huge consideration. It is what is the fundamental frequency of an object, and how do we avoid hitting any frequencies which will cause it to do that. because there are multiple orders of this. And so generally when you're designing, you're only considering the second and third order, just because that's the most likely ones to hit beyond the initial frequency. But it is.
Might interject here and say that what I think actually really what I was referring to, and this was the fundamental frequency is the frequency being played on the speaker, and the harmonic distortion in this case is additional overtones to what that fundamental frequency is that are produced as a distortion from the material or the system.
Gotcha.
So what I mean by second and third order here is that there's even and odd order distortion, and typically second and third order are the loudest after the fundamental, and so that's the ones that a lot of people pay attention to when they're trying to reduce harmonic distortion, because they tend to be the loudest. But sometimes it's fourth, fifth, sometimes seventh order distortion that needs to be paid attention to as well. So that's sort of what that's referring to there, is the harmonic distortion is something that you want to watch out for, because it's, you don't want to, if you're playing a note, you don't want to be playing its overtones. It will add this sort of we've probably all heard it with a lot of more recent production in music with like bass tones. When you hear the overtone there, sometimes it's nice for highlighting a fundamental, but you don't want your speaker doing that for you. You want that to be a part of the music production. The speaker should just be playing what the signal is. So that's what that's referring to there.
Yeah, sorry, I read into that backwards from the Nori perspective.
Right,
the fundamental frequencies have it echoing my brain. Yeah. So yeah, if you're designing like a car or something, avoid the fundamental frequency.
Yes, absolutely.
In the case of like the speakers, yeah, just account for it. It can be applied in different ways. And then nonlinearities, this is just kind of referring to, is it something we can easily model or not? So materials and just overall components, we try to make them as predictable as possible. We want to be able to say, yeah, that is going to act like this, but inevitably things go wrong with that. And so nonlinearities are kind of those non-modelable additions that don't just have like a linear reaction. Like there's more weird stuff going on with it. And yeah, operation.
Like a stress strain curve, right? Like, when a material starts like nonlinearities and like spring systems and stuff, right? It's just sort of when the thing starts not behaving in a linear fashion, and so you can still model it. It's more of but it requires more parameters to model, right? Because now it's a parabolic function or something, and
and also you get more towards like the limits of its use before it does very unhappy things.
Yeah.
So
bad things can happen.
Yeah, avoid nonlinearities essentially is the overarching statement of this. And
which is funny because you can't typically at all, but it's things you want to reduce. Everything's nonlinear, but we can approximate for most of it.
For sure. Love me some approximations. Yeah. So yeah, the limits are typically set where component behavior transitions from the linear behavior to the nonlinear. Now going into transducers, I think that this is a pretty good little diagram for you. So transducers essentially convert one form of energy to another. In this case, we're talking between kinetic or sound acoustic energy into electric energy. So for the case of a microphone, it's taking in that sound input and creating a current out of it. It's creating an electric signal out of it. Whereas with a speaker, it just does the exact opposite of that. It takes in this little signal and says, okay, this is how we will turn that into a physical motion that creates physical sound waves. And then
Cool.
Brian's going to take it over from here.
Cool. So, more specifically, kind of some of the terminology applied to how a speaker might be. So, and we have a nice little diagram too of sort of what's happening in the motor here down on the bottom right. But if you're familiar with your E&M stuff from Physics 3, you'll remember, a coil, or, a length of wire going through a magnetic field will result in a force that is normal to the right-hand rule, effectively, right? And so that's what's going on here. Is you have this length of wire that has a current running through it, and that's creating, if you pass an alternating current through it, it's going to either be attracted or repelled from this permanent magnet, since this electromagnet is sitting, or this coil is sitting on a suspended assembly that can move. So that's what's creating sort of your forward and backward motion. It's a basic linear motor. And so then what's happening is that motion is being translated to a diaphragm, a cone, and that's amplifying the sound wave even further. So that way you actually get good translation or good transductance into the air, more efficient transductance. So, if we look at it in basic frequencies, right, it's sort of like if you put a basic sine wave in there, you produce a certain tone. If you have more complex signals, then that's going to effectively follow whatever you'd see on, if you're looking at a signal on a oscilloscope, then the speaker cone is effectively following whatever that complex signal is. So that's what the sound wave is looking like as it's being reproduced in the air. Go to the next slide. So here's some of the more kind of specific terminology in a nice diagram as well. So we call the electromagnetic coil the voice coil, and so that coil is put onto a former. That's just the whatever non-conductive sort of structural component that is translating the motion of the coil to the diaphragm or the cone. And so then you have the cone there that's being suspended by both the surround and the spider. So the surround's job is to really seal the diaphragm, the front of the diaphragm off from the back of the diaphragm, and also to help center the cone. And then the spider is there to center the cone in a more aggressive way. It's a stiffer component, and it's acting as a restorative force in this sort of spring mass damper system. And so that's when you've stopped playing an electrical signal, the speaker will want to mechanically revert back to x equals 0 at rest. And so that's sort of what's going to control also what the general damping factor and kind of which is defined as a Q number. And so that's a major component in that, as well as the sort of overall weight of the system. And then within the motor, we've got sort of our basic ring magnet, the pole piece, which is conducting the flux. So it's conducting it across that gap that the voice coil's in to create a magnetic flux field that is perpendicular to the flow of current. And then the basket holding the whole thing together, just mainly for positioning. The idea is it should be a perfectly rigid sort of chassis, which it never quite is, but generally it does a good job. So we can go to the next slide. Some things to kind of be considering when it comes to transducers, which are sort of the heart and soul of the speaker. So ideally, we want the transducer to be a perfectly linear piston, but of course, systems are not linear. So typically what happens, the common failings of a transducer are either its materials as they start reaching the limits of acceleration. So if you've got your cone and it's got a certain mass to it and a certain stiffness to it, you're moving it back and forth quite quickly, especially when you get into those upper frequency ranges. If you think about 20 kilohertz, right? That's moving back and forth 20,000 times in 1 second. So the acceleration that a cone sees is well over 200 Gs at those frequencies. It's something I always like to brag about whenever I talk to, Air Force or NASA engineers. Um, but so that's typically is when you have your material moving that quickly, the stiffness sometimes just can't keep up, and so your material is going to start flexing in a way that's not predictable very easily without very advanced FEA sort of methods. So that's a very common material failure. Also, you can put too much current into your coil and melt it, which is not a great thing. So that would be another example of like material failure. Magnetic distortion, the fields are not perfect, so there's definitely, depending on the different types of magnets that are used or different types of ferrous flux conductors, they can introduce distortion that can result in audio distortion. And then also sort of just general mechanical limitations, which is sort of linked to material failure, but your surround can only stretch so much. It's made out of rubber and it's limited by its geometry, same with the spider. So that, that's kind of what we're talking about there when things are failing in a nonlinear fashion. And that results in a distorted signal. So in order to reduce those things, really what a transducer engineer is doing a lot of the times is choosing their materials carefully and then sort of the geometry of it. And really what that is, the third thing there is that you're choosing materials and geometry for a certain design. That's a more modern approach to transducer design, is not trying to make a general transducer that works just well for many things, but in the last 15 years, we've seen companies really designing transducers specifically for applications, for certain sizes of enclosures, for certain dispersions that are required. A lot of the new smart speakers they're actually designing them for material failure, where the cone is flexing because there's some benefit in terms of the dispersion of the sound, even though it's heavily distorted sound, it's dispersed. So sometimes you select your materials and geometry to actually fail, but it's purposely so. So it's all something that you would be playing with, kind of the situation that you're dealing with. Sometimes you want to be making the most badass speaker in the world that's super high performance, and so everything is optimized for the least distortion. But sometimes you also want to make a cheap speaker for a cheap product. So. And that kind of comes to the manufacturing aspect is depending on the price that you're looking for, you need to look at reasonable engineering tolerances. And if you're dealing with equipment in-house, you have to work with what you have available. Or if you're outsourcing, then you have to keep in mind what existing manufacturing processes are out there. And then you have to be able to produce it in a quick enough fashion for whatever your demand is. So that's something that kind of relates to takt time. If anyone here is familiar with industrial engineering, it's sort of looking at like how much demand do you have and can you produce that amount. If it takes 12 hours to make one speaker driver, it could be a really great speaker driver, but if you're charging, $60 for a product, it's not really feasible from a business standpoint. And in general, it's just I like to also think about like variability, part variability. A lot of speaker components, sometimes like the spider component is highly variable, up to I believe 20% variation in its mechanical properties. So you kind of have to keep that in mind of, for whatever my transducer is being used in, can it take this amount of variability from each part to part? I think the only people I know of who have done incredibly low variance conventional transducers is Apple. Apple's very good at that. They're annoyingly good at it, actually. But so, yeah, it's something to be considering in the overall design process if you were doing this for a professional process, in a job. So go to the next slide there. So here's some fun animations of some nonlinearities happening in speakers. On the bottom, we have a Klippel laser scan. So they take a laser interferometer and play a speaker driver at different frequencies and scan the entire cone. So this is exactly what's happening on the surface of the cone. So On the left, we can kind of see what happens when the acceleration exceeds the limit of the mechanical, well, of the material itself, the stiffness of the material. So you get this sort of ripple effect almost, and this is just one kind of breakup mode. That's what this is sort of effect is called, as the cone breaking up. And so this is just one. This would be a radial breakup mode, I believe. But you can also have oh gosh, it'd be radial, or yeah. Anyway, I'm forgetting all of my terms here, but. So what's happening there, right, is that now you've got certain areas on the cone that are moving backwards, while other areas of the cone are moving forwards, and so you end up with this huge phase distortion. But it sort of scatters the sound as well. So it's sometimes people design for that, which is weird, because then you get higher harmonic distortion typically and phase distortion, and which results in frequency response distortion. But sometimes you just kind of deal with it. And then on the right, we have sort of what it should look like if it was a perfect pistonic motion, where you have, just perfect, positive, negative pressure, everything's moving as one. In the top left, we kind of have an example of what happens when you don't pay attention to that sort of, more of what Holly was talking about, the idea of a fundamental frequency, a fundamental resonant frequency of a component. If you excite it, then it can induce reflections back into the cone that then distort the sound even further. Even if the cones would normally be operating pistonically, the surround sometimes can act in a way that does not make it easy to reproduce sound cleanly. Same with all other components. You have these sort of failures that you got to watch out for. If those failures are happening within the bandwidth that the speaker is playing. And then in the top right corner is showing the nonlinearities of the magnetic force of a motor. So sort of with x equals 0 being at rest, and then as you apply a current further out, you're moving further and further out away from 0. But you can see that the magnetic force is not the same for the entire range of motion, and so that can result in this sort of signal distortion where it starts almost soft clipping the signal. So that's something we call power compression, and that's a big deal for people who work with large signals, large format sounds, when people are really trying to pump concert level audio. They care about power distortion because you're typically running at the limits of the speaker. And so if you don't have linear magnetic force, then you end up with quite a lot of distortion. So, and then this can actually change over time as well as materials heat up. There's thermal compression as well. But those are just some examples. I could talk all day about nonlinearities. This is a very, very kind of brief overview of things, but yeah, I'm happy to go into more detail after the presentation if people have questions. So sort of like some general transducer categories. That's kind of funny. It's like speaker drivers are like sexuality. It's a spectrum. There's no classic definition of what a woofer mid-range tweeter is. You can use woofers as mid-ranges sometimes. You can use mid-ranges as tweeters sometimes, depending on the type of driver. I've seen woofers used as subwoofers. I've seen tweeters used as something called super tweeters. It's sort of, you use a driver for whatever bandwidth you need. They just tend to be optimized for certain bandwidths. If you're designing the driver yourself, you get to optimize that for what your application is. If you're working with something that you're buying off the shelf, like from Parts Express, then you have a certain driver that you can maybe use different sections of the bandwidth for depending on what your design is. But typically we see sort of subwoofers handling, nowadays with smaller satellite speakers, sometimes they pull up to 200 hertz. Typically, I define subwoofers as anything playing below 100 hertz. However, I've been working with some designs where I've got the subwoofer playing up to 280 hertz. So it's it's certainly not a hard and fast rule. Woofers and mid-ranges can kind of be used. There's also a term called mid-woofer, but it's the idea that, depending on how many drivers you have in the system, if it's a two-way design, it's typically a tweeter and a woofer. If it's a three-way, you have tweeter, mid-range, woofer. And if you have 26 drivers, then you just, I don't know, you can name them after different hurricanes or something. But yeah, so kind of like the general categories of what people are referring to when they talk about a tweeter, mid-range, woofer. Give you some ideas of those ranges. So when you're kind of trying to design the cabinet to put the driver into, so what the cabinet's doing, by the way, is its main function is really to provide some sort of baffle, some sort of separation between the front wave and back wave of the speaker. So if you've got a driver, you've got sound waves coming off the front and back of the cone. If we just had that vibrating in free space for any wavelength that approaches that is larger than what the diaphragm is, it's going to start wrapping around and canceling because you have 180-degree inverse coming off the back of the speaker. So what the cabinet's doing is providing a certain amount of separation to allow for those frequencies not to be canceled, so you can play down into those lower frequencies. However, you don't really want the cabinet to be resonant or adding an additional sound into there, right? The cabinet can act as a sound device in itself. So if you've got a resonant cabinet, then you could hear some of those harmonic frequencies and stuff. You can hear buzzing or something. Then that's not a good thing for your sound. And then additionally, you don't want the interior of the cabinet. You don't want stuff reflecting back onto the cone, because then that can create some sort of constructive or deconstructive interference on what's being played on the cone. So then that adds distortion. And then also, you don't really want to be overbuilding the thing. That's sort of like you want to find a happy medium, right? You want it to be rigid. You want it to be very well damped, unreflective, but also you got to make the thing, so it should be manufacturable. I think it's funny because I look at both of the examples I put on here, but and I would say that aluminum Magico speaker on the bottom left there is not a manufacturable design. It's actually quite overbuilt, in my opinion. So that would be an example of going a little extreme. But you can see what sort of those results are doing there. They've had some examples of different materials and different designs they used, and so you can see sort of the decay rate. You have in your XY axis sort of your frequency response and amplitude, and then in your Z axis sort of coming towards out of the screen, that's sort of time. And so it's showing the decay when you play a tone. How long does it take for it to decay? How well damped is this cabinet? And so you can see them sort of testing out different situations, and in the little Q5, what they ended up at, it ends up being very, very, very well damped. So that's sort of what the hope is for an ideal cabinet, is just something that doesn't have any resonance. It's just immediately dead right after. But then also on the other side here, I kind of feel a little bad because the person who did build this little homemade box on the bottom right, they did do one thing right, in my opinion, and that is that it's slightly trapezoidal. So that means that it will help reduce standing waves that could be in the box. Using non-parallel sides is a common way to reduce sort of standing resonant modes within the box that could color the sound. So go to the next slide there. So here's some kind of like examples of some acoustic topologies. I'm gonna go through the first 3 in a little more depth, or 4 actually. But and so I've got some pictures of the other ones as well. But you can use all different types of acoustic topologies to augment what the speaker driver itself would play on its own. The most, kind of some of the most common ones are the sealed ported designs. That's what 95% of the designs you see are. And then there's some kind of more fun ones. Infinite baffle is something that isn't common, but I would say the most common thing that you'd see it in is maybe like an in-wall speaker Transmission lines are very uncommon. There's maybe about 2 or 3 manufacturers that still make them. But they're an interesting study in what kind of like quarter wavelength amplification. But I'll go over that in a little bit. And then there's also the horns. At the time of the presentations we were pulling from, I didn't go too deeply into horns, and I'm actually working with horns a lot right now. So maybe we'll do another presentation on horns in the future because there's quite a lot of interesting stuff about them. But there, you can see some examples of common horn types in the top right, very top right. There's a tapped horn, and then there's a folded horn. So a folded horn is sort of the precursor to the tapped horn, where you've got this sort of exponential expansion, and you're trying to model the physical box over the as the expansion of a sound wave. And what this is doing is sort of just like when you cup your hands over your mouth, it helps amplify the sound because it directs all the acoustic energy into a single direction. So you can often get sometimes up to 6 to 12 dB improvement in efficiency. So it's very useful for usually a narrow bandwidth. They're difficult to design though. They're difficult to design properly, I should say. But very tactile, very good sort of bass chest feel. A tapped horn is sort of an advancement on that, made famous by Danley, and that's an interesting one where it uses sort of like quarter wavelength amplification with a horn geometry, sort of like a hybrid transmission line folded horn ish. So that's a common one, especially in like large format sound. And then bandpass is another one that you might see. It's very efficient. It adds quite a big boost because you're just exciting a Helmholtz resonator effectively. The problem is that it's also very bandwidth limited. So that means that you're going to get this very efficient bass frequency, but maybe playing from 40 hertz to 60 hertz or something like that, or 40 to 80, but not a very good wideband speaker. So that requires more drivers or more cabinets to be used to cover the full audible spectrum. So we'll go into some detail here about sealed and ported and a few other ones. So go to the next slide. So the sealed cabinet is sort of one of the oldest, I guess, like properly designed enclosures. It's sort of the beginning of intentional cabinet design. I think it was Edward Vilchner or something like that, and Henry Kloss developed it back in the 50s, 60s. Acoustic Research was one of the first companies to come out with these. And what was cool about this at the time is that the suspension components, the mechanical suspension components and speaker drivers, they just because of manufacturing limitations, they couldn't be that stiff. There was difficulties with them being stiff and still linear. So what this got around is it used the internal air pressure as a suspension component, and that helps damp the cone and improve the transient response. So that when you stop playing a sound, it comes to rest quicker, and so they're typically known to have really nice punchy sound. That's what a lot of people characterize them as, and they tend to be one of the smaller designs as well, which is nice if you're trying to design one of the like a small enclosure for a speaker. But anyway, yeah. So some of the kind of like pros about it are that it's really nice and easy to design and build. It's just a volume, so you can make the volume whatever shape you want. You can you can make as long as you have the same volume, you could be changing sort of the if the walls are parallel, if you want to kind of be designing for not having back reflections and all that. And you can really kind of vary that volume a little bit by about, I believe, 5%, and it shouldn't really affect the acoustic properties. So the beauty of that is if you're doing your own DIY build, you can add bracing in and not have to account for that in your acoustic simulations. You can kind of just be like, oh, cool, this is close enough, and I'm still going to get about the same output. In production, that means that you don't have to have as high of tolerances for if you're manufacturing it in volume. Another benefit is that it also, because it's sort of a sealed sort of spring component, it is excursion limiting. So that means if you have a driver that doesn't have a strong suspension, it can help limit the excursion for the amount of power you're putting into it. So that's good because you don't want to overwork your mechanical components of the speaker because things could break. And then it has a really nice smooth roll off as well. So that sort of it's very low phase distortion. It's I guess a good way of describing it is it has a natural roll off, as a lot of people describe it. So it's nice when they're designed well. However, it's typically hard to get a very wide bandwidth, especially low bass extension with sealed designs. And because you're just sealing the thing, you're wasting all the backwave energy. So in some designs where you're using the backwave energy, you can get way more efficiency out of this moving driver. Here you're throwing away all the kinetic energy coming off of the back. So that's kind of like the basic precursor to, I think, the like intelligent speaker design. Before the acoustic suspension speaker, people really just kind of guessed. They would just throw stuff in cabinets. They wouldn't seal them. They were leaky. Like some of the old Klipsch and Altec designs were very lucky in their design as opposed to engineered in their design. So yeah, that's kind of the precursor. So we can go to the next slide here. So kind of a more advanced design, which is probably one of the most common today. Sorry, excuse me. So the bass reflex design is interesting. It's using effectively a Helmholtz resonator to fill in for the speaker as the speaker driver's bass response starts rolling off. You can use the movement of the driver, even though it's still playing those lower frequencies, just not as loud. You can use the cabinet as sort of like this tunes device, just sort of like a Coke bottle, right? So you excite with a Coke bottle, you excite it with your breath, and you get this tone out of that. And so in this case, instead of your breath, you use the speaker driver, and so the port then starts taking over for it as the driver starts dropping off. What's cool about this is it really does allow you to extend the low frequency, like the abilities of the speaker, pretty far beyond what it would do on its own in a sealed configuration. So, and I have a comparison on the next slide, which I can show in a second. But however, the roll-off is much steeper. It's a fourth order roll-off, 24 dB per octave. So you kind of play down to a frequency, and then after that, it's like, oh, well, there's not much. It tends to be, but it is, higher efficiencies because you're not trying to overexert the driver. So you get some efficiency, some benefits there. However, the issue is that, since you're trying to excite this resonant system, the transient response and sort of the overall impedance curve, they really get worked pretty heavily. So the transient response tends to suck. And I don't know if there's probably a better explanation, but the way I like visualizing this is the lower you try to get this thing to play, because typically your transient response suffers the more you try to get it to play out of the band of the speaker. The time it takes, if you think about like blowing on a Coke bottle, it takes a second for that resonance to build. And that's the way I've kind of like visualized it when it came to a bass reflex design, is that it takes a second for kind of that low frequency response to build an amplitude. And so there's this temporal smear in the low frequencies then, and that can result in that muddy bass sound. And that's why some people, a lot of audiophiles, they tend to be like, oh, ported designs, they sound sloppy in the bass, which is typically true if you're a very critical listener. But I have heard some good ported designs. There's definitely some out there. I mean, some of the the Revel stuff that Harman does, it's pretty decent. Paradigm has some good designs as well, but they just all tend to suffer from that sort of that transient response issue. They're way more complex to design to. Not to us engineers, we're like, yes, this is a basic equation, Helmholtz. Yes, it's pretty easy for the DIY person as well. However, it's because it's more finicky to whatever the dimensions of the port length, port size, and the volume are. You have to be more precise with your calculations. You can't be adding in braces after the fact and just taking away volume. It will change your tuning frequency, which will change your overall frequency response. So it's a little more sensitive in that way. And then it also is, depending on if you use ports or something called a passive radiator, which I'll talk about in a second, um, they can be kind of noisy from turbulent flow. It's because you've got a port and you have air moving in and out of it. So if you calculate the Reynolds number, you can determine that it's typically turbulent flow. It's almost always turbulent flow, but you want it to be, lower turbulent flow, because if you have too high a velocity, then you'll end up with chuffing, the sort of like, kind of the like almost whistling sound. If there's too high a velocity in the port, then it's not laminar flow. So that's something that can be designed for as well. There's some pretty simple calculations typically in many of the design tools that are available. Now, there's also the variation called of a passive radiator, and this is actually one that has become really common in the past 10 years, I'd say. It's been around for forever. I mean, you can find designs as far back. I mean, Polk was doing as the Monitor 7 was a very popular passive radiator design, which I think was in the 80s. But what it is instead of using a port, you just use effectively a speaker driver without the motor on it. So you have a mass and spring system, and a little bit of damping as well. So, but it's just a basic resonant frequency calculation. So you've got your spring constant K and then your mass, and from that you can calculate your resonant frequency. So you can tune this passive radiator just by adding weight to it, and then that acts as sort of a port that resonates with whatever the volume is, and it gets excited by the active driver, and so then it starts taking over as the active driver isn't able to keep up. So the reason why this has become very common in the past 10 years, I'd say, is that think about a lot of those Bluetooth speakers that they want to have somewhat efficient low frequency output, but they also don't want water to be able to get into the thing because they don't want to put a hole in the box like a port, right? So for a lot of those like Ultimate Ears little Bluetooth speakers, they'll use passive radiators that create a bass reflex design, but allow them to be thrown into water or something like that, right? So that's a very good benefit of the radiator design. The problem is that you have to design it so that way it has more displacement ability. Technically, it should only have to match the displacement of the active driver, but typically you want to have, I think, at least 30 to 40% extra displacement available. So that way you're not at those nonlinear mechanical limits of the radiator design. So that's a fun one. It's really cool because you can pick up these components on Parts Express, like basic passive radiators, for sometimes as cheap as $10. So it's a fun thing to implement, and also it's kind of a cool thing to be like, it's being driven by the resonant frequency. It's a fun party trick. I've used it in conversation many times, but it still does suffer from those transient response issues, since it does take that sort of time to build the resonance on that surface. So yeah, that's probably one of the most popular design at this moment. Also because it is relatively simple to put together in mass once you have things figured out, as long as you're not changing tolerances too much. It's pretty easy to make. So yeah, we can go to the next slide. So here's kind of an example of like if you had a speaker driver and you tried it in both the ported and sealed configuration. And I'm assuming most of you should be familiar with frequency response curves, so I'm just going to assume that. But you can see how in a sealed configuration you have a much more gradual roll-off, but it starts way further up in the frequency response. Whereas with the ported design, this is the combined ported output. So this is summing the output of both the port and the speaker driver. You can see that port sort of really fills in as the sort of typical sealed configuration would be rolling off. It's not exactly what's happening, but it's sort of the visualization of a good visualization of what could be going on, sort of. But it's filling in, but it drops off much steeper. So you end up getting that lower frequency extension, but once you've reached your sort of low corner, that's about it. So very useful, especially in sort of like home theater subs. They like using ported designs because you can really get that nice low frequency kick and kind of punch to it, which is funny because it's actually a smeared transient, so it's not all that punchy. But they market it well. So yeah, that's kind of a good comparison there. And then so yeah, we'll talk about the infinite baffle. This is an interesting one. Mainly because this is a great way to get it's probably most used in measurements, actually. A common way of measuring kind of what a transducer is doing is you can drop it into an infinite baffle, which would be like cutting a hole in the wall and sticking a speaker driver in it. So it's a theoretically infinite baffle that separates a theoretically infinite volume on the back from a theoretically to whatever the listening environment is on the front. Of course, that's not really a thing. Over a certain size of volume, depending on what the driver is, I think it's like when you reach 5 times or 2 times the VAS, which is a parameter that's used in measuring speakers, then it starts acting as an infinite baffle. So the cool thing about an infinite baffle is that you don't get something called baffle step. Well, you don't have to compensate for the something called a baffle step. What's happening is if you have a baffle that is a certain length, right? If it's finite, then whatever the length of that is, the frequency that is that wavelength will start rolling off because it becomes omnidirectional. It's not reflected forward after that. So with thinner, with speakers that have smaller faceplates, smaller front baffles, they're going to start becoming omnidirectional at higher frequencies. So if you think about kind of like if you had a speaker in front of you and you started walking around the back side of it, you can still hear a lot of those kind of low and mid bass frequencies. And so those are sort of those omnidirectional frequencies. But because they're being played omnidirectionally, the energy is being dispersed throughout the entire room. And so it actually tends to sound like there's less output because it's not all being reflected forward towards the listener. So you have to do something called a baffle step compensation. And you have to either cut the high frequencies or boost the low frequencies. Typically, it's cutting the high frequencies if it's a passive design. So what's cool about infinite baffle is that doesn't happen. So you get this extra anywhere between 4 to 8 dB boost in efficiency in those really large wavelengths that typically would be wrapping around a smaller cabinet like a sealed or ported design. And so I've heard of people like dropping 18-inch subwoofers that cut holes in their floor in their living room somehow. And then they just drop these huge drivers in and they're getting really flat response down to like 10 hertz. Because they don't get that typical roll for these huge wavelengths. But it requires a room and it requires a wall. So it's just not a very practical thing for most speaker situations, unless if it's something like a living room, unless if it's something like an installed speaker. The other cool thing about it is there's theoretically no cabinet reflections, but that of course isn't true in any situation because usually if you're putting something in a wall, there's something behind that wall. So that's kind of like typically what you would see infinite baffles used for is either measuring transducers for just finding out the capability without an effect of a cabinet, or if it was an in-wall speaker. So move to the next slide. So I threw transmission line in here because it's kind of a very basic, it's like the most basic quarter wavelength acoustic topology. So that you could consider it compared to the other things we've looked at, it's the most advanced thing. But there's definitely more advanced designs out there now. like that tapped horn and some other ones from other manufacturers. So, but the transmission line is just a very basic one to kind of conceptualize. So if you just imagine the wave coming off of the back of the speaker, um, if it was played in a perfectly 180 degrees out of phase, which is what's happening, and you just pipe that to the front of the speaker, then it would make a cancellation, and so then you would have deconstructive interference. But if you were to offset that by 90 degrees, then you end up having constructive interference, and so at that certain tuned frequency. So what's happening in a transmission line is you look at the frequency you want to be boosting and sort of and kind of reinforcing with that constructive interference. Typically that's around the resonant frequency of the driver. And then you make a labyrinth, a path length. You mechanically delay the sound wave coming off of the back of the driver by a quarter of that wavelength. And then you pipe that out to the front of the speaker, or around the front of the speaker. And what that does is then it creates that constructive interference. And then typically, because there would be deconstructive interference in higher frequencies, you'd want to put in a lot of damping along the way to help take out those higher frequencies, so that way they don't make your frequency response suffer in the mid range. And this is the benefit of this really is over a ported design is typically it's a little bit slower roll off. It can be anywhere between, I guess, sort of second and fourth order, depending on the driver and the path length. But what it does is it creates a very smooth impedance curve as well. So it's nicer on the amplifier that's driving it, and it ends up being nicer on the driver in general. And it has pretty nice low frequency extension. I've heard of some people saying that it couples into rooms better. Like you don't end up with sort of these weird dips and peaks as much. I can see that might be a thing. People have proven it true and untrue. So I would say that it's a case by case basis. But it's not a very popular design because it is pretty complex to build. You have to build for 30 hertz, let's say, right? That's if you take a quarter of that, it's somewhere around like 8 feet. So you have to build a very long labyrinth. And typically it's done by folding it back and forth, and that requires a lot of internal sort of cabinet components. And so it's not very scalable for volume production, and that's why you don't see it as much. Bose was able to do it a little bit. They had some weird workarounds. Mostly, I think they were just using a lot of cheap labor. But they're like Bose, their Acoustimass sort of line, I believe. It's just basically a transmission line. So it's been used in some mass-produced stuff, but at this point, I think the only people really using it as a main design is PMC. It's their British speaker company that makes sort of like studio monitors and some high-end hi-fi. But generally, yeah, it's an interesting design that is a basic principle that can be used for amplifying, or even sometimes you do want to suck out certain frequencies if there are big peaks or something you want to take out. Then it's just quarter wavelength acoustic manipulation is a really powerful thing. So that's sort of the fun exotic one I like to bring up. But yeah, there's some cool new ones. Definitely, if you search through sort of like the general patent space in speakers, you can find, I mean, Sony's been doing some weird stuff, Function One, some other ones as well. So it's if you're interested in just crazy speaker designs, especially the like large format pro audio world has some really, really interesting ones. So I highly recommend checking that out, and I can discuss some of that a little bit later if people are interested. So yeah, that's a transmission line. You can go to the next slide. We have these videos for the manufacturing process, kind of like overview of how a transducer is made. It's a little bit of a long video. if people are interested in kind of if there's interest of everyone here of learning more about transducer manufacturing, I've got um, another presentation I could bring up. But I don't know. I feel like this presentations or this meeting is just better used if we perhaps have a discussion as opposed to watching a 12-minute video. So I think Holly will post this in the drive, and so if you're interested in watching this, I recommend doing so. It's a cool video.
Yeah, I'll send out the link via Slack later. And if any of you aren't on our Slack, or if you want this but don't want to be on our Slack, you can just go ahead and like shoot a message to me or Alex or our general audio engineering society email, or any of our social medias as well. Like any way of contacting us to let us know, hey, I want to be on the Slack, or hey, I don't want to be on the Slack, but I do want the link to this. Oh, did not mean play.
Oops. Preview.
Preview. Okay.
There you go. Cool. So, and for some, and kind of to end, I kind of like after talking about a bunch of technical stuff about how you can design for getting certain types of sounds. I love reminding people that at the end of the day, a lot of the time psychoacoustics play a larger factor than any technical thing you could design for. So it's interesting. Sort of psychoacoustics is something that's applied to a lot of different situations. In this case, we're talking about how the mental perception of what a speaker should sound like will influence the way that you hear it sound. So sometimes when like that's due to the visual design. This little quote we have here is sort of that's from someone who she was or she's a orchestral person. She either plays something or she composes stuff. I forget. But she did this study on kind of like how the visual representation of musical performances can affect the sound, even for people who really care about like what that content is. Just the visual representation will influence the way that they actually kind of like hear and enjoy it. So that's very true for speakers as well. Is the visual representation can massively influence. Well, not massively, I should say, but it can influence the way that you hear or perceive sort of the sound. And sort of the really fun way of looking at that, if you go to the next slide, is that there was this study done, the Rainbow Effect, in 2001, where they did a bunch of listening tests with the same exact speaker, but they just put different colored grills on the front, and and then they kind of got listening feedback from a bunch of different people. And typically they saw that red speakers were perceived to have better bass. Blue speakers had kind of more clarity and openness. Yellow speakers were perceived to be more loud and have more treble. And then green were kind of more of the balanced sounding one to people. So even just the color of the speaker can kind of influence the way that you think something sounds. So it's something something to think about. That's something that I'm thinking about a lot right now. Is in the speakers I'm designing, is that we want you want to create a design that is nice to look at, because then it should influence your mind to think that it's nice sounding. So if you're designing a product, that's very important. If you're designing it for yourself, it's also nice to be like, yeah, I want to look at the thing. I made it, and don't want it to look like trash. And because of that, you tend to appreciate the sounds more. It's sort of like because there's effort put into it. There's also the like general IKEA principle of if you make it or if you put effort into it, you tend to put more value into it. So that's another fun one too. Is sometimes DIY people read into liking their designs better than manufactured designs because they've put effort into it. That's also part of the reason why people tend to think vinyl sounds better, which sometimes it does, sometimes it doesn't. But because of the act of like, taking the vinyl out of the cover and, putting the needle on the record and stuff, it's you put this effort into it. And so you tend to listen to it more, you tend to engage with it more. And so in audio, the amount of engagement, I would say, is really what tends to, it's a good factor in what people are going to take notice of in the sound. So Yeah, that's kind of I think that's where we're sort of ending. I don't think there's another slide after this, maybe.
We have a fake
Oh yeah.
acoustic side.
Holly found this. This is crazy.
I was looking for a good infographic, and this is what I found. And it wasn't quite what we were going for, but I really liked the way that it was laid out, just in like how things are like emphasized. It goes from you hear a sound to your body takes action. And I just really appreciate that. And I want you guys to as well, after knowing what we meant by psychoacoustics, as opposed to triggering a fight or flight response, I think, is how they were perceiving that. Yeah, so.
I will say, I mean, this is I've seen the effect of good sound on moving bodies. Let's say it's people tend to dance more.
Well, this can be taken through like the concert perspective, or it can be taken through like the thriller movie perspective, where like they play those really low bass notes that kind of get you like, oh, I need to run.
Oh yeah, infrasonic sound. Yeah.
Good stuff. All right, I'm gonna go ahead and stop the recording now, and then we can go ahead and have a little bit of like Q&A discussion, like however you guys want to lay that out.